So now let's talk about carbon, another element essential to the backbones of the biomolecules. What makes carbon so special is its electronic structure. What makes carbon so special is its valence electrons. These are the electrons in the outermost energy level of the atom. These allow carbon to form single, double, or triple covalent bonds with itself or other non-metal elements. We're going to see covalent bond with carbon. It's going to form the backbone of all the biomolecules we're going to talk about. So what makes carbon so special is the 4 valence electrons. So let's look at the simplest carbon-based molecules, the hydrocarbons. This is just carbon and hydrogen. They are nonpolar. There are hydrophobic properties, which means they don't like water. There's very intermolecular forces. The only ones we see are van der Waals forces. These are attractive forces only based upon the random distribution of electrons. Because electrons are consistently moving, we're going to find that the movement of these electrons can cause momentary dipoles that do not stay. So you get all these different shapes. You can have double bonds, you can have chains, you can have ring structures with carbon. But the most interesting things come when we start replacing these hydrogens with other elements, other covalently bonded elements such as oxygen and sulfur and phosphorus. So because of this, when we start replacing these hydrogens, we get an infinite variety of molecules that can be made with a carbon backbone. You can have multiple bonds, branches, chains, ring structures. We're going to look at isomers, how you can have the same chemical formula but different structures, and functional groups. Some interesting things start to happen, and we change the properties of a compound by adding different chemical groups on there. It's going to give polar or ionic properties to something that started out as being hydrophobic. And molecular structure affects biological function. So when we start changing around the molecule and we start adding these different groups, we're going to see that it's going to affect the biological function of that molecule. So let's start off with some isomers. Same chemical formula, different structure, and each of these structures will have different chemical properties. For example, basic isomers of propanol. Simple carbon compound. You have 3 carbons to the compound and an oxygen. So you have different isomers. Say if we count up the hydrogens, the oxygen, and the carbons in this compound, you end up with the same chemical formula. However, there are 3 different possible structures which would give each of these compounds unique properties, all because of where that oxygen is. There are also geometric isomers. Once again, these have the same chemical formula. However, we're going to see that this plays a huge role when we start talking about fatty acids. A cis functional group means that it's on the same side. So looking at the chloroethylene, the dichloroethane, the chlorines are on the same side of the molecule. The double bonds between the carbons cannot rotate. So the molecule is balanced out, it's linear. The trans-functional groups means the functional groups are on the opposite sides. So in the trans 1,2-dichloroethane molecule, the chlorine atoms are on opposite sides. This is going to cause a bend in the molecule like in the oleic acid. This is going to have a vital role in the functioning of lipids in a biological system. In the last video, we will discuss isomers and why they are important to biological systems.